So today my presentation topic is automated crane-lift path planning using modified particle swarm optimization for high-rise modular integrated construction. My name is Aimin, and I'm now a PhD student. My supervisor is Professor Wei Pan. So firstly, I would like to introduce my research background. As we know, modular integrated construction is most advanced offsite technology. So from these two pictures on the top left, you can find that MIC modules are much heavier and larger than conventional construction components and materials. But the crane-lift executions are heavily reliant on operators' subjective judgment, which turns out to be time-consuming and error-prone. So it is critical but challenging to install MIC modules efficiently and safely. And automatic crane-lift path planning has been regarded as a very effective way to solve these problems. And these methods can be grouped into three categories. The first kind of category is the node-based algorithms, including the digextras and SDAs. But these algorithms are high time complexity. And the second kind of algorithm is the sampling-based algorithms. For example, the rapid exploring random tree and its variants. But the lifting trajectory is typically prone to more turns and twists. And the third one is the metric heuristics. And we found that genetic algorithms occupied most of the research, but other bio-inspired algorithms, such as particle swarm optimization, were hard to find in crane-lift execution fields. So our research group proposed a modified PSO to find a collision-free crane-lift path, and the source code of PSO was illustrated on the bottom right. And here is the research methodology. And from the picture of the top left is our research design containing three parts. The first is the background examination, is to conduct a comprehensive literature review and interview with professionals such as crane operators, project manager, project team, and so on and so forth. And second is the modeling environment development using modeling methods and metric heuristics. And the third is and finally, the third is to verify our proposed method. Here, I would like to highlight that our proposed method is the first of its kind to introduce PSO for crane-lift path planning, and it is an initial attempt of planning crane-lift paths in MIC projects. And the picture on the on the bottom left is the system architecture of our crane-lift path planning. It includes the building modeling environment and mathematical modeling environment and an output. I will give you more details in the following slides. And the picture on the bottom right is the workflow of the proposed PSO algorithm. It includes the classical three parts: the input, processing, and the output. And after inputting all these parameters, PSO can calculate fitness function automatically and update personal and global best and update the position and velocity of these particles. And after the algorithm reaches its maximum iteration, it will stop and conduct poster crane-lift issues. So now I'll give you more details about the system development process. Just as mentioned before, the modeling process is very important because it includes the development of the building modeling environment and the mathematical modeling environment, mainly including three sub-steps. And step one is to create the beam models of the MIC buildings and the tower cranes. And step two is to simplify the beam models as the OBB models for collision detection. And step 3 is to build a mathematical representation of the OBB models by reading the geometry information. And also, I would like to highlight that we also consider 3 major components to conduct the crane lifter issues. And the first major component is the tower crane operation strategy. Because if we want to achieve automatic crane lift path planning, we need to understand how the tower crane, hoist the lifting module. So after conducting literature review and interview with crane operators, the contractors, we designed this kind of crane operation strategy from the start configuration to the end configuration. And I also want to say that the between the adjacent configurations is the age. And the second component is the correlation between loading capacity and working radius. And most of the previous publications ignore the correlation between the loading capacity and working radius. And crane manufacturers may provide the table like this. This table includes the discrete data of loading capacity and working radius. But if we receive the loading capacity, but this value cannot be found in the table, it will take some time to calculate the working radius, and the result may not be very reasonable. So we adopted the cubic spline interpolation method to automatically automatically compute the working radius. And the third part is the fitness function. It is very commonly in bio-inspired algorithms, and is very important for measuring the crane lifter path, the cost path. And our designed fitness function include 3 metrics. Metric R1 represents the hoisting time between adjacent configurations. Therefore, TS is the total hoisting time of the among all these configurations. And metric R2 represents the hoisting distance between adjacent configurations. Therefore, TS denotes the total hoisting distance among all these configurations. R3 is set for conductor collision detection. So CS is the number of collision points. So the problem of finding the optimized crane lift path can be transformed to calculate the minimum FS. So we utilized a real-life MIC project to verify our proposed method. From these 2 tables on the left, is the parameters before conducting our algorithm, and the results is the rest of this slide. So from this picture on the top right, you can find that PXO can find the optimized result very quickly at around 120 when iteration set as 300. And also we give a field example. When the iteration set as 100, it cannot guarantee to find the optimized result at any time. And the 3 pictures in the middle comprehensively analyze the performance of PSO. So from figure A, it can be found that the best rate and convergence rate increases with iterations. And the figure B shows that PSO starts to converge when generation reaches 100 or so. Therefore, the minimum cost amount increases nearly linearly. And figure 3 illustrates the difference of minimum, maximum, average cost among various iterations, indicating that PSO is very stable. And these 6 pictures, illustrates our 6 experimental scenarios. And the first three pictures on the left is the end configuration without nearby obstacles. And the last three pictures on the right is the end configuration with nearby obstacles. So you can find that no matter what the end configuration with or without nearby obstacles, it can find an optimized clearance-free path easily. And these path trajectories are smooth and easy to operate for clearing operators. So our findings and conclusions are summarized below. Our paper has proposed a modified PSO algorithm to automatically conduct clearing lift path planning for high-rise MIC. And the research is the first of its kind to introduce PSO for clearing lift path planning, and it's an initial and successful attempt of planning clearing lift paths in MIC projects. And also, the proposed algorithm can generate a clearance-free clearing lift path with a small population size and a few iterations, and the lifting trajectory is found to be smooth and easy to operate. And our future works are to optimize the proposed algorithm to perform multiple clearing path planning in MIC projects, and to use various sensors to obtain real-time environmental information, update the operating status of tile cranes, and carry out dynamic clearing lift path replanning. And finally, I would like to acknowledge our two sponsors. The one is Research Impact Fund of the Hong Kong Research Grants Council. And the second one is the Strategic Public Policies Research Funding Scheme from the Policy Innovation and Coordination Office of the Government of Hong Kong Special Administrative Region. Thank you very much.